going. So it's great to see a group of people, and this is really for students and postdocs as much as for the faculty members. We'll be sort of around and attending numerous talks like that. And science is sometimes a little bit accidental. I actually met Lei for the first time maybe 2.5 years ago in the APS March meeting. I just remember it was a Friday afternoon, but his talk was really among the most impressive ones through the whole week. So I sort of kind of came up and talked with him, and then mentioned sort of got research interested. Why don't you come to the talk at Brown? So 2.5 years later, here he is. I don't actually remember exactly what he talked about 2.5 years ago. Maybe it's the same thing, but still doesn't matter. But just looking over his title and the initial center, there's a very long, a lot of detailed information. This one is a simplified version, but very briefly, Lei did his undergraduate at Colorado State University, and then went to Stanford for a PhD, and then basically took a faculty position right after that. So you missed something scientifically important for a lot of physicists, which is postdoctoral training, right? Which means you spend years just to do work. There's no training on teaching at all, and then all of a sudden you become a professor. But for him, he missed those training, he just became a professor right away, and he has been on the faculty at the University of Pittsburgh for the past 5 years. Maybe the first 3 years didn't meet anybody, right, during the pandemic. So now he's going to tell us about his work, really range of interesting topics involving fluid dynamics and energy, and then climate science as well. So we're just going to let Lei give his presentation. But finally, I have to say, it was a total surprise for me to find out that we actually grew up in the same hometown. Home city. It's not a hometown, but same home province. But I did not know until like 10 minutes ago. That's sort of one of the accidents in life. With that said, I'm sure you're going to give a good talk. All right.
Of course. Yeah, when we grabbed the tea, we mentioned about the hometown. We said, okay, we're from the same place. Okay. So today we are going to talk something called manipulating spectral energy flux across scales. This looks a little weird. Hopefully after 1 hour, it can make more sense to you. So first of all, a brief introduction of my lab. My lab, now my focus, gradually focusing on 2 things. One is two-way coupling between swimmers and a background flow. I'm specifically interested in swimmers with a particle Reynolds number between 1 to 100, something like that. Not too small, not too large, in the middle. And specifically, I study how swimmers affect the background flow, which means how swimmers generate turbulence, weak turbulence, right? And also how background flow affects swimmers, how they align the swimmers, things like that. I'm working both in 2 and 3 dimensions. Another thing is something new I developed recently. I will present this mainly, which is flow manipulation. So let's get started. So, in 3 dimensions, when you think about the 3-dimensional turbulence, the energy goes from large scale to small scales, right? As predicted long time ago, a decade ago, right? And in 2 dimensions, the net direction is from small scale to large scale in terms of energy fluxes. So then we have a question, which is, can we manipulate these energy flux directions? So if you think about the kinetic energy density as a function of wave number, which is 1 over length, right? And if you, in the turbulent flow, if you remove degrees of freedom, eventually, because this system is a highly nonlinear coupled system, you will have an extra term that describes the degrees of freedom that's being removed and the degrees of freedom that is retained, how they communicate energy. So in a large eddy simulation setup, you think about Navier-Stokes equation. If you low-pass filter it, and you multiply the equation with a low-pass filter to velocity, you have the evolution equation of the kinetic energy. And then eventually, the term that describes the energy flux between a certain scale, the cutoff length scale, is something like this. So that, this is the energy flux between the scale that is being removed and the scale that has been retained. So if you look carefully about this term, It is essentially the inner product between two second-order tensors, right? And the geometry matters, right? So if they are aligned, they are anti-aligned, or they are randomly aligned, you will have a different Q. Most all of the examples I talked today will be in 2D. I'm moving to 3D. In 2D, it's even simpler because your eigenframe have two orthogonal eigenvectors, right? And in 2D, you can determine the angle within the alignment between tensors with only one angle. And then you can simply write your Q as the multiplication of the scalars. This is a positive eigenvalue of stress, positive eigenvalue of stress, strain rate, and the angle between them, cosine to theta. So we have before that, I will show you, this is experimental data. So the black arrows are measured velocity. And the color is the localized energy flux Q. And this is the field of extensional direction of strain rate tensor, rate of strain tensor. The color is its eigenvalue magnitude. This is corresponding to same instance. This is a extensional direction of the stress tensor. The background color is the eigenvalue of the stress tensor. So you see that if this is an inverse flux, where you have a energy flux have a negative sign. You see, you zoom in, you will have what? You will have angle alignment smaller than pi over 4. So you plug it here, smaller than pi over 4, you have a negative sign. Things like that. Nothing new here. Then we have a hypothesis, which is that if you drive the flow generically, and you measure the flow with sufficient amount of resolution, and then you calculate the stress tensor, rate of strain tensor, right? They have alignment. Their alignment determine not only the magnitude, but also the direction of the energy flux. Suppose I can perturb the flow at small physical perturbations that somehow can be written as filtered small-scale quantity, tau ij, small-scale stress. Then, essentially, I have ability to control the energy flux, right? Because, this is how I say all stresses are created equal. No matter whether that stress is self-organized, generated by self-organization, you drive the flow very hard, you have a stress tensor, or I intentionally perturb it with certain directional bias, right? So they should be mathematically equal, and then they should be coupled with each other to generate energy flux. So with this hypothesis, what we do is that we try to use a small rod, put it on a linear actuator, move back and forth to drag the flow in a directionally biased manner. And with very simple derivation, you can show that if you use a cutoff length scale that is sufficiently larger than the rod size, the perturbation size, then the extensional direction of the resulting flow, the stress tensor of the resulting flow, is aligned with the moving direction. So then, if I put a shear flow, so this is a shear flow, and I put a rod moving at a different orientation, I should generate energy flux with different directions. So that's the idea. Then what we do is in the lab, we generate a thin layer flow, electromagnetically driven flow. Essentially, you have a raw array of magnets with a positive up, array positive down, and you have a DC current through it. So the black arrows are actually the velocity field measured, downsampled for clarity. And the magenta arrow is essentially the extensional direction of the rate of strain tensor. So that's a well-organized rate of strain tensor. That's one part. You have Sij, right? Then we put an array of rods and put it on a linear actuator and move back and forth. And in the quiescent fluid, we drive the rod array back and forth. According to our simple derivation, the resulting tau ij's extensional direction should align with the moving direction, which is true here. So now we have rate of strain tensor. We have stress tensor. According to that equation, right? The alignment. If I turn both the current on, generated shear, and turn the linear actuator on, it should have a different direction of energy flux according to that equation. So let's try out. So this is an experiment. The raw image that you have an array of rods, and then these are the tracers. If you analyze this, you will get something like this. We have three control cases. One is called shear, which is just the shear itself. And another is a shear with a steel rod array to preclude the possibility that the manipulation is due to additional boundary conditions. And another is moving rod array with no shear, just in case that the rod itself generates some kind of like a weak turbulence. And we have three different cases. We define theta as a mechanical angle, which is the alignment between the rod moving direction and the shear's extensional direction. So these angles you can determine before you do the experiment, a priori, right? And then this is a result with the control cases. You have a pretty symmetrical angle distribution. This is a theta L. Remember, this is an alignment between tensor. That is a filtered quantity. And they are pretty symmetrical around pi/4, where you, on average, you have zero energy flux, right? Because you have a cosine 2 theta. And the mechanical angle change the tensor orientation significantly. And this is a normalized energy flux as a function of time. You see, it's going up and down because we're driving the linear actuator driving the rods. But you have different directions of energy flux. And we also plotted the normalized energy flux as a function of cutoff length scales. You see the same thing. In forward energy flux, inverse energy flux, almost like a weak no energy flux here. So before talking about this, you can see these are the video. The color is instantaneous and local energy flux. So to be specific, this one is special one because in 2D, naturally energy goes inversely. But this one is a quite weakly 2D turbulent flow with an opposite direction of energy flux. So this is something strange. And up to now, we were thinking, my student and I, actually my first PhD student did it, thinking, okay, maybe this is too good to be true. Did we just alter the direction? So we want to double check. So all these measurements are based on filter because that's essentially like a weighted average, based on weighted average around the point. So we do something different. We look at the structure function, cellular structure function. That's the lowest one that can give you, meaningful direction, right? So that essentially, in the calculation sense, it takes the information between different scales based on displacement. So we want to double check that. We see that they also have a distinct directions. So then we talked to our collaborator who worked on direct numerical simulation. They did the exact same thing and see exact the same thing, except that the sine wave is much nicer than experiment. And we did do one more thing. Actually, here is a pi. Pi and the q are the same. I forgot to change this. So y-axis is energy flux. X-axis, the simulation can alter the mechanical angle very accurately. So you see that this energy flux as a function of a mechanical angle that you can determine a priori show a sine wave which corresponds to that cosine 2 theta there. So up to now, hopefully, I convince you we somehow in 2D we manipulated the direction of energy flux. And something more is that this one I call this, I just named this kind of turbulence called this useless turbulence because it looks very busy, but on average, no net energy flux. They're useless. So my newest PhD student now is working on manipulating three-dimensional turbulence. We are trying to generate a three-dimensional turbulence, hopefully with like more than 1 decade of inertial range with inverse energy flux. That's something we are doing.
Can I ask a question?
Of course.
Maybe I blinked. In your previous slide was the experimental case.
Yeah, this is experiments.
And this is two-dimensional turbulence.
Yeah, weak turbulence.
How did you do that?
This one?
Yeah. Is it with
a manipulation. With a manipulation. Yeah.
No, but it's with the small device, the microchip that you showed before.
This is not. This is not the microchip. This is pretty large. This is 80 centimeters.
Okay.
80 centimeters.
All right.
Yeah.
So it's 2D because you're just taking a slice of
a single layer. I make the width here is roughly like 15 to 20 centimeters, depends on my student how they put, and the thickness is only like a 4 to 5 millimeters. So it's a quasi-2D
I see.
flow. Yeah.
I got it. Thanks.
Very good clarification.
Also, quick question: what's the size of your the selection that you take for analysis? Like you have like a 6x6. You have it like a,
Yeah.
You analyze these images, right? But like the boundary, you start to like it looks a lot of the signals at the boundary, right?
Yeah. So the thing is that the question is how large. You can tell that the distance between rods is 2 centimeters. So the size is like, I would say 6 centimeters. The thing is that we do the filtering because at the edge you have a filter, you have to step out. So we trim all the edge so that you have even on the edge when you do the filtering you have the information. And why it's on the edge? Because here on the edge the shear have a much stronger magnitude. In the center, essentially that's the shear with the same shear rate but almost zero velocity. That's my explanation. Question over there?
Yes. How is the entropy here? Because 2D turbulence entropy shows 4 cascades. So
Yeah.
say similarly, entropy is affected by this rod.
Entropy, that's a very good question. I try to do entropy because this manipulation, if you think about the scalar transport equation, I can also manipulate that, but that will be like between 2 vectors. And entropy, the specific device is not very good for entropy. If I do that, want to do that, I have to build a soft film because entropy typically go to small scales, and my thickness is like 4 to 5 millimeters. So it's already too large. So the thin layer does not have a very good entropy dynamics. Yeah. Theoretically, you can do the same thing for entropy, but this device cannot do that. Okay. Hopefully okay. They're good in touch. Okay. After this, because everything is like in the web number space, I want to say, okay, whether the manipulation of energy is consistent with the idea of viscosity. So the simplest definition of viscosity is you ask me, what's viscosity? I would say, I'm an engineer. I will give you a very superficial definition, which is something that makes the shear weaker, right? So you have 2 fluid parcels. If they either go left or right, the slow one will slow the fast part. Faster will speed up the slow part, so that the shear will be weakened. So, so this one is forward energy flux case. This direction is derived from it's originated from this directional perturbation. It originated from Navier-Stokes equation, right? But if I kick this low y momentum parcel this way, eventually the resulting force will be this. Initially, if they just go to the right, it will have a small y momentum. But here, by kicking specifically in this direction, it will have a negative y momentum. This is positive viscosity that even slow the shear even further. So it's consistent with our energy flux stuff, right? If I perturb in this orientation, if you kick this way, if you kick hard enough, eventually your resulting velocity will be have a higher momentum for this fluid parcel once it travels here. So this will make the shear even stronger. So that's something called negative viscosity, and that's associated with inverse energy flux typically. So that makes sense. Makes me feel good. And yeah. So actually, I will talk about this, and this. So actually, I sent out to the reviewer. The reviewer said, "Okay, it's a very nice, interesting one, but rather it's interesting rather than useful." But I'm preparing 3 papers. So I typically copy paste those papers and submit it back to the referee. Okay, I will talk about this, and this simply because this one I haven't done that. It's just at the hypothesis stage. So then the question is, can I make something called the turbulence at a low Reynolds-Number? How do I define Reynolds-Number? The first thing, okay. So I define Reynolds-Number in 2 dimensions based on the frictional constant. So it's a friction Reynolds-Number because in 2D, energy dissipated through friction. So it's like inertia over friction dissipation instead of like inertia over viscous dissipation. And how do I define turbulence? Because turbulence, you don't have a well-agreed definition. I define turbulence here as a flow with multi-scale and a strong enough energy flux between different scales. So back to this equation. If you want to generate turbulence at a low Reynolds number, I can simply say, okay, I want to increase this term, but without increasing Reynolds number, or increase Reynolds number but just a little bit. What can I do? Lambda tau is a big hope, because this is a small scale quantity. At a low Reynolds number, everything's laminar. You don't have a small scale quantity. If I intentionally add small scale quantities to it, this term will surge. Lambda s, you can't do anything because it's a large scale quantity. If you want to increase that, that will definitely increase the Reynolds number a lot. And the cosine 2 theta is a hope. In a pretty well developed two-dimensional turbulence, cosine 2 theta is 2.27%, according to our previous measurement. Actually, we define this as the efficiency of a turbulent cascade initially. But so there's a hope. As you reduce the Reynolds number, typically this angle will become closer and closer to pi over 4, which give you zero efficiency. If I can intentionally perturb the flow in a right direction to increase this angle either to 0 or to pi over 2, then the cosine 2 theta will have like efficiency almost like 1 or -1, so that you can increase Q. So we did it. So we tried two types of flow. One is a shear, one is a cellular. And this is a different color. This is a horizontal is a different color than scales. Y is energy flux pi. Now I change the symbol because it's a different paper. Divided by I should keep the symbol same, but anyway, normalized by frictional dissipation. And these two are before my perturbation laminar flow. The extensional direction of two tensors, you see, it's exactly pi over 4, very close to pi over 4, their alignment. But after I use a rod to gently perturb it, they align. So hopefully, you see that the energy flux from background, very small, increased. And I should go back. So cellular flow is in the red, similar things happen. And this is the angle statistics. This is the angle between two eigenframes. And you see after I perturb it, it's very biased towards 0 or pi over 4. And this is the efficiency, cosine 2 theta. So this is efficiency before. After I perturb it, it's something like this. They have a very close Reynolds number. Actually, to be honest, they are different sets. Because once you perturb, your Reynolds number increase. So I do an array of those and pick one perturbed, pick one unperturbed with the closest Reynolds number. So you see that efficiency increase to one end of the spectrum, right? After you perturb. This is perturbed. Okay, this is the conclusion of this project, not this talk. So you have energy flux, normalized energy flux for different Reynolds numbers. So if you look at the legend, the background flow is almost like 0. And pure perturbation, you just have a rod moving in without any background flow, very small energy flux. You perturb it with pi over 4, very small energy flux. You perturb with pi either 0, cosine 2 theta is 1, or pi over 2, cosine 2 theta -1. You have a surge in energy flux. So all the blue ones are shear, and the red one are the cellular flow. So something we do is here. We use energy flux normalized by corresponding background flow. You see that around the Reynolds number, around 1, is RE alpha. You have like 2 orders of magnitude increase in energy flux. And then we look at the right-hand side of that equation, one by one. So sigma is the strain rate tensor's eigenvalue. So you see that if I perturb the flow, my strain rate tensor's eigenvalue actually decreases a little bit. That makes sense because Reynolds strain tensor is a large-scale quantity. You perturb the large-scale thing. And the big surge is this. This is a stress tensor. Imagine you have a laminar flow, low Reynolds number. You have no small-scale quantities. Right? In the shear, everyone just move in a straight line. After you perturb, the stress tensor's eigenvalue increase significantly here. This is one part that makes this happen. And also, eta is cosine to theta. So with laminar flow, your angle between the two eigenframes is pi/4. So cosine 2 theta almost 0. And after you perturb it, the efficiency go, I would say, roughly to 90%. With the help of this and this, you get this. And we compare to the literature. So x-axis here is the kinetic energy you have. Because in the literature, they typically don't report their alpha, their friction constants. So I assume, by using E, I assume that they have a similar alpha. Actually, a lot of the paper was from my advisor. I used the exact device as his. So this should be the similar alpha. So x-axis is roughly Reynolds number, you can think. And the y-axis is the energy flux magnitude. So from the literature, you see that as your kinetic energy increase, you gradually have an increase of energy flux, right? And with our perturbed case, you have an increased energy flux right up. So typically in the literature, they typically claim, okay, if my energy flux is larger than this value, I consider it as a turbulence. So that's my rationale to claim it as, Low-Reynolds-Number turbulence. Yeah, so these are some picture I asked my student to quickly produce. So they have same Reynolds number, but this one is very well organized. This is complicated. Same Reynolds number, low Reynolds number, we perturb it. It's complicated. Okay, so then I'm very sorry that I did not say Monica because this is about biogenic turbulence. Monica's here? No. Okay, no. Okay. Hopefully she can watch the recording. So biogenic turbulence, there are two parallel lines of argument where the animals can mix ocean, right? One side is, about the energy. We'll focus about the energy here. So a lot of people believe that if you have a dense aggregation of zooplankton, right, they observe a strong energy dissipation with a zooplankton. This is by Kraichnan published in Science. Later on, he keep measure the energy dissipation rate near the dense aggregation of zooplankton, and he published the annual review. And he said this, which is a strong association with zooplankton and energy dissipation, corresponds to a frequency of occurrence of less than 4%, suggesting that turbulence production by marine biosphere is not sufficient. Okay, by rejecting his science, he published an annual review. Yeah. Anyway, but I think based on what we did before, when we think about how small swimmers generate the turbulence, you should not focus on swimmer itself. I think in all the research before, when they study biogenic turbulence, they assume that its ability are inherent to the swimmer. So they study swimmers in quiescent fluid. But think about it, if you replace the rod by a swimmer, the orientation matters. The background shear matters, right? So this is something I think I can contribute here. So I call this, Kraichna's dilemma. I invented this word. Why? You have a group of zooplankton. They are more or less, have a similar power output from the group, but only small fraction of time you have a strong energy dissipation, right? They are same. The reason is what? They borrow energy from mean flow. It's not you have a 4% of the group, they are athletes. They are same. Their power output is same. But due to the geometric alignment, they borrow energy from mean flow. Okay, so I redo the hypothesis, replace anything by swimmer, about the rod by swimmer, and using the same experimental setup. Now it's like in a shear, I have a swimmer swimming through. I did not use an array of a swimmer because they are very hard to control. So one is very hard.
Is this still like your 4 millimeter?
Yeah, still
Okay.
4 millimeter. So the length of this swimmer is like roughly 1 centimeter, less than 1 centimeter here in this case. So this is my shear. The black arrows are the velocity vector, And this orientation is an extensional direction from experiment. And the same hypothesis should apply because when you have a swimmer that generates perturbation along its body length, so this theta s, which is also mechanical angle between the swimming orientation, and the local extensional direction of the shear should determine the direction and the magnitude of energy flux, right? So we do the experiment. So this is I already said this, right? So this theta s can be replaced. This theta L can be replaced by this theta S roughly. And this is a prediction, right? You know the trigonometry is very elementary. And you see, that's true. You have a same swimmer. Maybe they are not the same swimmer. They are similar swimmer, but with different orientation. You measure the flow, you low pass filter it, you calculate energy flux. You have different directions. And with pi over 4 case, you have almost like a zero energy flux. So this is a talk I give to Professor Tom. Okay. So we do this again with different color of length scales. We see similar thing. So this simply shows that when we study biogenic turbulence, we should not focus on the swimmer itself. The ability to generate turbulence is not inherent to the swimmer, but also it's a geometry alignment with background flow and the background flow strength.
How do you make your brine stream follow a particular direction just by chance, or just do thousands of them and pick the typical good ones?
Yeah, I will give all the credit to my PhD student.
I'm sure you did. Yeah.
So essentially, they put the swimmer outside the field of view and let him swim. Most of them don't swim inside the image domain, but some of them do.
Yep.
And then he just recording, and pick up the one with a straight line with certain angle. So that's the same. Essentially, you have like 10 hours of recording, and eventually you get a bunch of trajectories. So that's the same. So the way to explain Cousin's dilemma, you have a group of swimmers more or less doing similar amount of power, right?
Yes.
Why only small amount of time you see strong energy dissipation? This is because most of the time the swimmers are swarming. They have a different orientation, right? Their polarization is 0. And then you have at the surface of the ocean, you have a shear. So they cancel out. Only small fraction of time, you have a relatively strong polarization. And that alignment is good enough with the local extensional direction to generate energy dissipation. And that power, energy dissipation rate, have a unit of power, right? Have a dimensional power. The extra power is from inflow. I will show more data later on, and you will see. So that's the same. Yeah. Then we also discuss whether this swimmer. I will be quick here because I have one more thing to show. If you have a different direction of energy flux, that should manifest it as the shear's strength, right? So instead of swimmer, because I cannot control a group of swimmers, then my student will be crazy. So I use a syringe pump with a needle. You see, needle with a different orientation, and to mimic the wake behind the swimmer. And you see different the energy flux as a function of different cutoff lengths follow the same rule, except for pi roughly equals to 4. It has inverse energy flux, simply because you have a jet and then it expands. Naturally, in 2D, you have an inverse flux. For the jet that is expanding, they do not have a well-defined length, like a rod or swimmer. So you see, the conclusion is that with the inverse flux, you have an enhanced shear. For the flux, you have a weakened shear. So it has a manifestation in physical space. Okay, then I talked to Aker last year, and we actually have one collaborative proposal. So previous ones simply shows that orientation matters. You should not focus on the swimmer, you should focus on the orientation. This project is about how small is too small. People believe that in biogenic turbulence area, when swimmer is smaller than certain threshold, universal threshold, then they cannot generate sustainable or noticeable biogenic turbulence, right? My answer is no. You don't have a universal threshold. You have to consider the background shear, because your perturbation is weak, your tau ij is weak, but your Sij is strong, eventually your energy flux should be good. And also the orientation. So this is from Acre's simulation. We have the strain rate strengths, the shear strengths, and also the length, assuming swimmer swims at 1 body length per second. So, and this is a energy flux. This is at very early stage. So, if the universal, cutoff length or threshold exists, this contour line of energy flux should be vertical, but we show that it's not. At the 3.54 millimeter is very tilted. Maybe we should extend a little more. So the conclusion is that the background shear strength is important, orientation is important. So we're still working on this one. Okay, so hopefully I've convinced you we manipulate the energy flux. We generate somehow at a low Reynolds number around 1. When inertia is still not negligible but not dominant, we generate turbulence. And also biogenic turbulence, our idea is that you should not focus on swimmer itself. And all the rest of, I think most of the previous literature only focus on swimmer, which should also focus on the background flow. And then lastly, I scale up to manipulate geophysical Lagrangian coherent structure, roughly like a few kilometers to 10 kilometers. So what's a Lagrangian coherent structure? Okay, Lagrangian coherent structure is, specifically here is attracting hyperbolic Lagrangian coherent structure. So essentially, the simplest way to think about it is a transport barrier. This is a virtual die. If you move, this is from experimental data. If you integrate for like 280 over times, the virtual die simply elongated and folded, but does not penetrate. So in the coastal area, this is not from experiment. This is schematic. I hired an artist to draw it. So in the coastal area, this LCS, Lagrangian transport barrier, is very troublesome because it blocks the transport. For example, you have a desalination plant. You want to discharge some of the brine, they get stuck. So the idea is that if you can break the LCS, you can significantly enhance the coastal health. How can we use what we learned before to do that? Think about it. This is in physical space. This is in terms of energy. You have a large scale, which is a LCS scale structure. It should have some kind of energy. If I can smartly perturb a little bit to generate additional forward energy flux, then this large pile of energy should be weakened, be smaller. And then as a result, the LCS should be altered somehow. So that's the idea. This is the hypothesis. Then we go to Taylor-Green flow, and Taylor-Green flow is analytical. Naturally, this is from experiments. It's not an analytical flow. It has a attracting LCS, repelling LCS. So we are focusing on this attracting LCS. So with some very simple, like a 1 page or 1.5 page derivation and analysis, you can show that you can use like 10 to the -3 of the background power to alter that LCS by generating strong energy flux. The energy flux is comparable to the power to drive that flow, assuming a constant alpha. Anyway, so we did the experiment again. So this is a cellular flow that we generated, 4 cell, and here there is a attracting LCS, which is here. This shows the velocity field as a black arrow, and also the magenta arrow is a local extensional direction of rate of strain tensor. And you see, we have a hope, which is here. We have a well-organized rate of strain tensor, and we have the background color is the eigenvalue. We have a good eigenvalue. We have a larger eigenvalue, which can potentially give us larger energy flux to deplete the energy. Okay. So we perturb it. This is a inverse flux, neutral flux, and forward flux with a different perturbation, different angle. This is our old stuff, right? We have done this a lot in the previous talks. And we do see energy flux manipulated successfully here with the control cases here. And this is the same. The horizontal is the cutoff length corresponding to this red line. Y-axis is the P power normalized by the power from the rod array. So rod array has a 1, but with 1 certain unit amount of perturbation, you can generate a flux that is 3 times. So that's something that when I mentioned about a swimmer, right? You have a certain group, you have a swimmer with a power P, but it can have a distribution of a few P, XP, X greater than 0, or greater than 1, right? So that's the same. You have a certain amount of power from the rod array, and then you can generate much, actually should not say much, a few times more of energy flux, addition of energy flux, and then to control break an LCS with the length, with power that is much larger than the rod array. And then we see this. So this is a theta equal to 0. This is theta equals to pi over 4. Theta equals to pi over 2. So you see, it's a rod with the same amount of power input, but different geometry. It results in different direction of energy flux. As a manifestation in physical space, it has a different result. Pi over 2, additional energy towards small scales. So the energy piled up in the large scale being depleted to small scales. As a manifestation, the LCS originally is a flat vertical line, become fragmented and shows small scale structures. Okay, so then we think, okay, we are going to break and transport the barrier LCS on the order of like 10 kilometers. Even though I can use 1% of energy to break it, that's still a lot of energy, right? So I'm thinking about using passive way to break it. How do we do that? Oh, before I will show you this. Before we move on to the passive strategy, this is a mass flux across this from left to right, right? So this is the furthest reach of the vertical LCS because our LCS is slightly time dependent. It's wiggling a little bit. So this is the furthest reach. For the background flow, of course, is a transport barrier. You release a tracer on the left-hand side, nothing penetrates by definition. Theta equals to 0, inverse energy flux case. You don't deplete energy to small scales. Stop here. Neutral case, some leak. Forward case to small scales, you have a significant amount of transport across the transport barrier. Okay, then we think about the passive strategy. It's inspired by satellite image. If you just browse online, see those wind turbines. Actually, wind turbine should have a foundation in the ocean, right? And you have a tide going through it. And once tide going through it, you generate a wake. Those wake are small scale compared to those transport barriers. And those wake are directionally biased because it's at a certain direction. So that directionally biased perturbation should be written as tau ij as before, right? So we did an analog experiment. I have the cellular flow running, and then I have a wave generator here, generate a wave, going through this field. Without the rod, the LCS stays here. With rod, it's fragmented. And we look at the energy flux. Without the rod, you have a wave going through, not much energy flux. With rod, because you have a small scale energy perturbation, forward energy flux, corresponding to the breaking of a large scale structure.
The rods are fixed.
Rods are fixed, yeah. So this is the analog experiment. And then we find the satellite data. We are lucky that in the outlet of the Thames River, there's an array called the London array. And we have data before and after it's built. So London array, these wind turbines are here. These are the wind turbines. The yellow line is well-known, well-agreed, I would say, persistent ocean front, which is an approximation location of the transport barrier. Before, you see, that, as compared to the later one show much more fine-scale structures reminiscent of this one. Yeah, and then we use an objective front tracking algorithm to track them, and use box counting method to do the box counting. That's typically used for to calculate approximate the fractal dimension. And you see that afterward, you have slightly but consistently higher slope, indicating more complex front. So the difference in slope is around 10%. So one thing is that before and after we have a different satellite. One of the satellite dead, so the new satellite have a high resolution. So we got the data and we downgrade these ones to that one, so they are comparable, and then do all this analysis just in case that this fine structure is simply because of the higher resolution. But by downgrading, they are comparable, and then you have a 10% of difference. Okay, so these are the talks. Pretty much is a full paper. One about the manipulating. One is this. One is this. One is this. Something that I'm doing before that. Something I'm doing now. First of all, scale up this into 3D. Into 3D, you have one more dimension, but the complexity is much more complex. You have a 2 tensor frame, and then you have to have 3 angles to describe their alignment, and you cannot factor out these angles mathematically. So, but we have design a device to manipulate the 3-dimensional turbulent flows, energy flux. And another thing is we are trying to use the same principle of this to break tornado. We are building an indoor tornado box, still on the construction, and then we will use some needle to dispense some very small jet, essentially scale everything down, to see whether we can break the structural integrity of the tornado. Maybe later on we can do some field work on that. And yeah, so, and also we are continuing to push on this osmos too small idea to show that there's no universal minimum size to generate turbulence. And yeah, this is all the people working on this project, my students and the collaborators. And these are the QR code for the paper. I have some not yet out, but these are the ones out. I'm happy to take any questions.
Very interesting talk. Questions? Yes.
Thank you for a very interesting talk, and I think this is really interesting idea to breaking down LCS using the forcing. I have one question about that. So, if you can break the LCS with large scale motion with the positive energy flux and that's dissipated, but still there are small scale LCS can show up, and then because of motion of the LCS, small scale LCS, mass transfer can be enhanced, but still there are some barriers, small scale barriers over the plane. So yeah, how is there any way to evaluate to make it really mixing the?
You mean to handle the small scale?
Yeah,
LCS?
so large scale is breaking into small scale LCS, but still there is an LCS there. So
yeah,
is there any yeah?
I think the thing is that which length scale you are focusing on. If you have a large scale transport barrier, essentially by definition, if that's a true mathematical barrier, no mass flux, and you break through it, and gradually they have if you have these boundaries here with the correct tide direction, so this leaking effect is continuous. So that will alleviate, mitigate a lot of environmental problems already. We don't plan to totally break the LCS. For example, this one, this ocean front, this is 1 kilometer. It's like more than 10 kilometers, and we are getting this for essentially free. This boundary is like 10 meters in diameter. I don't think we want to totally break them. That will cause a lot of energy. Yeah.
Yeah. So if I understand what you're doing correctly, is essentially you look for places where the stress is high, there's like some critical point in your flow where you wiggle it in just the right direction to break it up, right? Mm-hmm. And I guess so. If you do that and then you do your experiments, you see that, well, I made the perturbation at kind of this I guess, weak point of my flow, and and then it breaks it up. But how do you know that it doesn't if I believe that everything should flow to large scales in 2D, how do you know that that structure doesn't just reconstitute somewhere else in your flow?
Yeah, that's a very good question. So I think the thing is that you have two mechanisms to dissipate the energy.
Right.
One is at small scale you have a viscous dissipation. At large scale you have a friction.
Yes.
In traditional 2D turbulence, you have forward and inverse energy flux. But if you look at instantaneous energy flux, you have a lot of so-called backscatter to
Right.
forward energy flux.
Yes, that's right.
So those energy are eventually dissipated by viscous dissipation. So if I reverse the direction, there's no problem dissipating it. So I think the nature finds its way.
I see.
Yeah.
Maybe it's a follow-up question, but so your artifact, your magic of this is that you can alter the structure of turbulence by injecting some directionality of some intruder, right? But so that only works if you have a background flow,
Yeah.
correct?
Yes.
If you have isotropic turbulence, this shouldn't work. Is that correct?
That theoretically should not work. I think then you really need an iterative feedback controller, right? Locally, if you can quickly analyze the flow, see, okay, there is a well-aligned rate of strength tensor here, I
Okay.
perturb. You need to iteratively do that.
Right.
Yeah.
Right. But in your case, in your experiments, is you impose a background flow
Yeah,
and then you
perturb
do
it.
the smart or
Perturbation,
trajectory
yeah.
that okay.
Yeah, in real turbulence, it will be hard. It will be a feedback controller.
Yeah. Okay. All right. Yeah. Good.
Yeah. The thing is that I want to generate three-dimensional flow with inverse energy flux and with enough inertial subrange so that
Yes.
I can test all this traditional theory. Because traditionally we don't have this creature. We only have one creature forward energy flux. All the theory was built on that. But if I have a new creature, which is different, I can test all the theory.
Interesting. I thought most engineers don't care about theories. They want like practical applications. So this LCS, right? It's fascinating, this manifold thing, right?
Yep.
So one way thinking about application, I don't know how the implications are like, fish farming or something, like in this area, right? You need something to help to break this manifold, right?
Yeah.
If you have like fish going around, it can help mixing. Maybe, you have some nutrient distribution altered by this or shaped by this kind of manifolds, separation into separate chambers. Maybe it has some useful thing for fish to explore it. Some kind of application, I don't know exactly what, but I'm thinking about in this type of flow pattern stuff could be really of practical use.
Actually, everything here initiated from studying swimmer. Because no one in the middle of nowhere is thinking, okay, I want to manipulate energy flux directions.
Yes.
Right? I study swimmer, I try to do energy budget, every single time is different. Then I just put one swimmer with a share, and I study, and I find, okay, and I form a hypothesis, and then everything else follows. So.
Cool. Yes, Bob.
May I?
Absolutely.
So I know, and one of you guys, I'm sorry, it's not. I should apologize for her not being here, but she used this. She guided the brine shrimp with light. Did you try that to make them do what you want them to do? Because
Yeah, this is experimental detail. So when Monica did that, he has a 2014 POF. He guided the flow is on average. Actually, when you look at the swimmer, they all also different directions. So,
but if you just do one, maybe you can trick the brine shrimp just to follow the light.
I guess it will also just do random zigzagging. And another thing is that when you shine a light at the bottom of the tank, you will have a reflection. So you will have eventually two directions. One goes to the reflection, one goes to the true light. So it's initially my plan was use a white paper and use a projector to project the patterns to control them. But eventually it does not work out.
It didn't work out. Okay.
Yeah. So,
I guess on a simpler vein, is it possible to use some I confess I'm not in biophysics, but that's magnetotactic stuff to apply a magnetic field and force swimmers to go in a certain direction?
Maybe I haven't tried that.
Right.
Yeah.
Yeah. Interesting. Yeah.
Don't forget about these complicated animals. Just do robots, right? Just
Yeah,
make
robots.
them swim in the way you want.
And that's why he built so many robots.
Yeah. I mean, magnetotactic bacteria maybe
Mhm.
they're really interesting species to study because magnetic field, right? Can
Right, you can just
apply in
tell
a
them
They go the way
what-
they
Yeah.
go.
intuitively. You can. They come in different sizes too. Some have these aggregates, different shape.
Right, and you could get away. You don't have to have your grad students watch
Find
10
another
hours.
10,000. You can make them all go in one direction.
Well, that's a different length scale, right?
And it's
I
a
mean,
different size.
Yeah.
Sure.
On that note, the universal size, right?
Yeah.
I mean, at some length scale, it becomes almost academic, right?
Yeah,
Isn't
yeah,
it?
yeah.
Like, doesn't there like a length scale appear where it seems like basically universal? I mean, you would argue the slope is finite.
Yeah, yeah. So you also have to look at the S and also
Yeah.
look at the theta.
Yes.
Yeah.
So specifically, we're looking from here to here, somewhere here.
That makes total sense. Yeah. But I mean, like down at like micrometers.
Micrometer,
It's like-
all the effect will disappear because that Sij tau ij coming from advection term.
Mm.
As your Reynolds number is negligible, this tensor geometry idea is negligible.
Yeah.
So my low Reynolds number is still at a finite Reynolds number,
Mhm.
not like a 0.001.
Yeah.
Yep, magnetic robots. That's the way to do it. I know some of them.
Okay, one more question over there.
Yeah, actually, thank you. Great talk. On slide 30, I think it was 35.
Okay.
Can I ask exactly what? No, maybe it was the one where we were at the kilometer scale and we were looking at the wave fronts. I don't.
Yes. The last ones. Yeah.
This one, yeah. What kind of tracking algorithm did you use? You mentioned some kind of.
This one. I mean, front tracking.
Yeah, was there like some? Okay.
The front tracking name actually my my student did that. It's
Is it the same student that before or another student?
same student.
Oh, wow.
This is my first PhD student. Only the Low-Reynolds-Number turbulence is my third PhD student in his first year. Everything else is mostly my first PhD student. Oh, the collaboration with Aker is my second PhD student. Okay, anyway. So the question is front tracking. Actually, to be honest, I don't exactly remember the name.
Yeah.
But that's used in pretty standard, used in medical application. They have an image. They try to track the vessel, which have a line direction. I think it's like they look at the intensity field and they look at the eigenvectors and then do the tracking. But I don't remember the name.
Mhm.
It's published. You can look at this paper. It's
Oh,
in,
let me. Yeah,
it's
because
in,
I was about to draw similarity.
sorry, it's not published. It's,
Okay.
it's a third one. But we're preparing for that.
Okay.
The name is starting with F, but I don't remember the name.
Okay.
But it's used for medical application.
I was
when you
about to
track
say
the
it looked like
vessel.
medical blood flow tracking.
Maybe I ask one more question.
Okay.
So I guess you can compensate like the size with density too. Have you thought about doing it with some high density swimmers?
Yeah,
things
I
like
think,
that?
yeah.
We'll talk about bacteria turbulence, right? And then
Yes,
in this
yes.
case, they have high density bacteria. suspension.
Previous work, my PhD committee member John DeVry, actually Monica's PhD advisor, in 2018, he has an idea which is like a group of centimeter scale zooplankton moving together. They can be a group organism to generate length scale at the group scale instead of individual scale. So they have shown that. Yeah. So that's possible.
Cool. Good. In the interest of time, I think we will just thank the speaker again. And,